So, good morning, everyone. It's good to be with all of you once again. I'm excited. We're going to be finishing up our chapter on multiple integrals today. And I don't know about you, but it's been a fun chapter with a lot of kind of cool pictures and some kind of sweet little applications. And we're ending with this kind of cool little bit about the change of variables. But at the same time, no doubt, I think that I and perhaps some of you are looking forward to the change of pace that will happen when we move in back to chapter 10 and talk about sequences and infinite series. It's a little bit of an infinite commercial break, if you will, in the middle of our class. But let's not get ahead of ourselves. All right. When last we saw our intrepid heroes, we had introduced this idea of evaluating a multiple integral using a change of variables. But throughout, we had left our questions with this scaling factor. In our first example, we'd found the scaling factor geometrically, but we didn't have any sort of formula, if you will, for finding that scaling factor. So I thought that we could begin by going back to that first example and looking at how we would find that scaling factor algebraically. It's not really algebra, it's using calculus, but in a formulaic manner. And then again, continue on and show further examples of how we can find that scaling factor and how we would then implement it into our integrations. Let me switch over to my doc cam. You may remember this question from yesterday, where we were trying to integrate this between these two planes, and the region over which we were integrating was this kind of cockeyed square diamond shaped thing. And we created a substitution. U was x plus y, v was y minus x. This changed our bounds. We set up the integral, and we knew that there was going to be this scaling factor needed. And so we did some geometry, finding that the area of the original space was 200, the area of the new space was 400. We found our scaling factor was the area of the original space divided by the area of the new space, and that gave us the 1/2, which was our scaling factor. We turned around and we implemented this. Here's our new limits of integration with respect to uv. Our z's changed with the substitution. We were finding a volume, so we had an integrand of 1, and then we plugged in our scaling factor that we had just found and went through the whole integration and found the volume was 2000. Yay, that's all wonderful, except for the fact that right here in the middle, we had to find the area of these two regions, and it happened that they were both squares, so it was pretty easy. But what if they hadn't been squares? So enter the Jacobian. So the scaling factor that we are interested in is this thing called the Jacobian. And specifically, it's the magnitude of the Jacobian, the absolute value of the Jacobian. So to find the Jacobian, we remember that our u is x plus y and our v is y minus x. And the formula for the Jacobian of uv with respect to xy would be the partial of u with respect to x, partial of u with respect to y, partial of v with respect to x, partial of v with respect to y. And then, does anyone remember what those little bars represent in this case?
It's a determinant.
That's a determinant, exactly. And I'm trying to think, some of you have had linear algebra last quarter, so you definitely would have seen determinants. Have you gotten to determinants in linear algebra this quarter? Probably not.
We also used them in differential equations.
Okay, also used them in differential equations. For everyone else, you might not have studied them directly or calculated them directly, but a place where you would have used them would have been calculating the cross product. So the cross product would be a 3x3 determinant. So we're finding the determinant of this thing. Our ux would be the derivative of u with respect to x. That's the 1. Uy, derivative of u with respect to y, 1. Vx, -1. Vy, 1. And then, as you may recall, to find the determinant of a 2x2 matrix, you would multiply the main diagonal, 1 times 1, and then subtract the off diagonal. So this would be 1 times 1 minus 1 times -1. And that's where the 2 comes from. So this is saying that the area in the UV world is twice the area in the XY world. So this is the determinant of UV with respect to XY.
Math is getting cool again.
Yes, it is. Okay, let's see if that worked. Okay. Keep going. Okay. So if we solve for x and y, so we take these equations and instead of having it here solve for u and v, if we solve for x and y, we would get that x is equal to half u minus half v, y is equal to half u plus half v. And now we can find the determinant. What is this one? This is the Jacobian of xy with respect to uv. Jacobian of xy with respect to uv. And so this time now I'm looking for the partial of x with respect to u, partial of x with respect to v, et cetera, et cetera. And notice that when I calculate out that Jacobian, or sorry, that Jacobian, I end up coming up with a 1/2, which is the reciprocal of what I got when I found the Jacobian the other direction. Sort of makes sense. The scaling factor is going to be an inverse. Question, Jason?
Oh, no, I'm good.
Oh, Enrique?
Yeah, could you just say that in words one more time?
So the Jacobian here is going to represent the scaling factor that we care about. And the Jacobian, notice in the top case, we have the u's and v's in the numerator and the x's and y's in the denominator. Below, we have the x's and y's in the numerator, the u's and v's in the denominator. And so the scaling factor is going to be, the scaling factors are going to be reciprocals of each other, as we discussed yesterday, because in one case, you're switching from uv to xy. In the other case, you're switching from xy to uv. Did that help?
Yes, thank you.
Very good. All right. Are there questions about how to set up this Jacobian formula? One piece of good news about this formula is that you could also do the transpose. So if we did like ux and we did uy and vx and vy, it would work the same way. Furthermore, if you swapped your u's and v's, it would work, although we have to add one more thing to this concept in order for it to work. So the good news is this is actually a relatively error-proof formula. If you switch things around and you don't remember which is where, it usually works. If you swap your u's and v's, that works as well. It's going to be okay. So that's the first part of the formula, any questions for on how to calculate the determinant? Do people understand, based on the calculations, where the 2 and or the 1/2 are coming from?
I'm kind of confused with the setup of the equations.
Here?
Yeah.
That's a good question. So you're asking, where did those come from?
Yeah.
Okay, good question. So we have up here a system of 2 equations and actually it's 2 equations and 4 unknowns. At the moment, it's solved for u equals v equals. But we could come through here and we could solve for our x's and solve for our y's. And that's what I have below. Good news. In general, you don't have to do that because of the fact that these 2 results are reciprocals. So in general, at least in the questions that we're going to talk about in class today, if your equations are solved for uv, you can just find your Jacobian of uv with respect to xy, and then if you need the other one, just look at the reciprocal of what you're given. If you prefer, you could do a whole bunch of algebra, and you do probably substitution or elimination in order to solve for x and y. Does that answer your question, Joseph?
Yeah, that helps.
Very good. Cool. So all of this explains, I hope, where the scaling factor of 1/2 comes from, with just one little detail to add. That is right at the very top. Notice I have the statement on magnitude. So this bit right here, this is the Jacobian. I can't type. So this is the Jacobian. And what you're going to want is you're going to want the absolute value of that Jacobian. You'll notice that in the example that we're looking at here, the Jacobian is positive, and so the absolute value didn't make a difference. But if you happen to have swapped your u's and v's, you'd come out with a -2 here, and the absolute value would kind of undo that negation. So again, the scaling factor, it's not quite the Jacobian, it's actually the absolute value or the magnitude of the Jacobian. And it's just something to remember if it comes up in a question. Ready to do another example?
A question.
Go ahead, Melissa.
So for the problems that we're doing, would we need to find it in both ways, like in terms of x and y and in terms of u and v, or is it just 2 different ways that you could do it?
This is 2 different ways that you can do it. I'm just trying to show you the relationship between the 2.
Oh, okay, thank you.
So this is like most of mathematics. It's all about freedom and personal preference. So you can do this whichever way you want, whichever way you prefer. Some ways may require a few extra steps on the back end, but it's all about freedom and personal preference.
Okay.
Very good. The moderator in the background is muttering threats about my understanding of mathematics. So I want to briefly talk about the theory here. If you go to the book, there is a long derivation of where this formula comes from, and I simply want to point to one little piece of it that'll actually come up and be a little bit helpful to us later. In order for this to work, basically what we do is we take these funky little patches. It ends up being called a patch. And we say that patch is approximately a parallelogram. I don't want to be handwriting here. So it's approximately a parallelogram. You may or may not recall from Calculus 3 that you can find the area of a parallelogram using a cross product, finding the cross product and then the magnitude of that cross product. And so this is the long derivation. You can go through it if you want to see all the hairy details, but I think the short version is that this gets justified by approximating patches with parallelograms, and to find the area of a parallelogram, you need a determinant. And that's kind of the connection that's there. Second connection I want to make is going the other direction. About half of you, I think, are taking linear algebra right now. For those of you in linear, at some point you're going to come up and you're going to start taking determinants, and you'll learn about them. The main application of determinants in linear algebra is towards finding eigenvalues and then eigenvectors, which is pretty cool stuff. But if you want to visualize what a determinant represents, you can visualize the determinant as being the scaling factor of a linear transformation. Again, you can visualize a determinant as the scaling factor of a linear transformation. And so kind of between what you get in this class and what you get in linear, and then some of the applications that you see in differential equations, you see that that determinant has a whole bunch of different uses, but it always ends up being something about a transformation, and always ends up being something about a scaling factor, sometimes in a nonlinear place, but of a linear transformation. So I hope that context helps you understand why it is that the Jacobian is defined as we discussed. So when we were working on this yesterday, we had a couple of examples that we set up and we left without a specific scaling factor. So I'd like to continue those questions and see if we can work them through to their completion. So in example 2, we had this double integral of sine x squared plus 4y squared dA, and we were looking across the region D, which was in the first quadrant, enclosed by this ellipse. And so we did this little substitution where we let u equal x and v equal 2y, which turned our 9x squared plus 4y squared into the unit circle. And so our integral is now going to be the double integral across the first quadrant part of the unit disk. And then we've got a sine u squared plus v squared. There's a scaling factor that we need in here. And then we're going to have a dA. This is a dA prime because it's now going to be with respect to uv instead of with respect to xy. So we'd set up our integral. Now we know how to find scaling factors. So let's see if we can finish this stuff out. So we have that we want to find the scaling factor. So we have that u was equal to 3x and v was equal to 2y. So this tells us that the Jacobian of uv with respect to xy is going to be, I'm going to just repeat the formula so you get practice, is going to be partial of u with respect to x, partial of u with respect to y, partial of v with respect to x, partial of v with respect to y. Partial of u with respect to x is 3. Partial of u with respect to y is 0. Partial of v with respect to x, 0. Partial of v with respect to y is
2.
Happy 2. So this is the scaling factor if we started at uv and went to xy. but we're going the other direction. What we want is the Jacobian of xy with respect to uv. We want to start at xy and end in the uv world. And so what's this Jacobian going to be equal to?
1/6.
1/6. So this is our Jacobian. Our scaling factor is going to equal the absolute value of 1/6, which is 1/6, but I want to make a big deal about the absolute value so that you don't get derailed or surprised if it happens to change on you somewhere down the road. So let's see, how would we put all this together? So this tells us that our integral is the double integral of sine u squared plus v squared times 1/6 dA prime, and then we're just in the region that's in the first quadrant part of the unit disk. This is all very circular, so how would you suggest that we integrate this?
Polar.
Polar. Good call. So let's switch to polar.
So y equals to square root of, u equals to square root of 1 minus v square.
Oh,
Or
let's
switch
not.
to polar coordinate.
Yeah,
Oh,
let's not work that hard.
Oh yeah, polar coordinate will be easy then.
So this is going to become a sine of r squared times a 1/6, and then we're going to have our r dr d theta. Exactly, good call. And then our r's are going to go from 0 to 1 because this is the unit disk. And then we're only in the first quadrant, so our thetas are going to go 0 to pi/2. At this stage, it's just a bunch of writing. So the 1/6 can come out. There's no thetas anywhere, so we know we're going to have a pi/2 out front. Antiderivative of sine r squared times r is going to be negative 1/2 cosine r squared from 0 to 1 minus pi/24 times, looks like cosine of 1 minus 1. Questions? Very good. Oh, go ahead, Devin.
Yeah, I've just got a question. For like the presentations and stuff, are you all right with us just like flying past like the integration parts like d theta, since we already knew that it was going to be pi/2? It like in the presentations, are you fine with us just like not necessarily showing all of that since we already know?
You know, like in this part right here.
Yeah.
Yeah. Yeah, my general rule is that if I can do something in my head, it doesn't, without sweating or without writing it down, then I'm usually okay if you could do it without writing it down as well, or just saying it. And that would be true in the presentations. I figure if I can't figure it out by writing it down, then or explaining it, then I would expect that you would explain it or write it down. Does that seem like a somewhat, it's not perfectly objective, but a somewhat reasonable explanation?
Yeah, thank you.
Cool. Good question. All right. Let me do another example and then maybe well, boy, there's just so many examples and so much stuff to do. We'll see what happens. Let's just dive into a second example. So you may recall this was our example 3 from yesterday. And kind of the same thing is going on, where we set up a u and a v, and now we simply need to find that scaling factor. And so if we want to find the scaling factor, we're going to need to find the Jacobian of uv with respect to xy. And that's going to be ux, uy, vx, vy, 1, minus 2, 3, minus 1, which is a funny way of writing -1 plus 6 or 5. So what's the scaling factor that we want?
Don't we want to go from x's to u's?
We want to go from x's to u's, exactly.
The 1/5?
1/5?
Exactly, 1/5. So what we want is the Jacobian of xy with respect to uv, which is going to be 1/5. And so our scaling factor is going to equal the absolute value. Again, I want to make a big deal of this absolute value because sometimes if you forget about it, you can end up with the opposite sign at the end. So the absolute value of whatever we found here.
So why do we always flip the Jacobian again?
Because basically think about the way scaling works, that doubling things or having things is just a matter of which direction you're going.
Mm.
And so this 5 represents what would be the scaling if we started in a UV world and ended in an XY world.
Oh, but we're starting in an XY world.
But we're starting in an XY world and ending in a UV world.
Okay, yeah.
And by convention, are you doing the first one first and then the second one, or is this like an order that we go through?
That's a great question. The reason why... Hold on to that question. Let me do the rest of my lecture out of order.
Got it.
And I think I can answer that question by showing you a different example.
Okay.
Yeah, it's a good question. So if we put this integral together, this tells us that I is equal to the double integral from 0 to 4, 1 to 8 of u over v times 1/5 dv du. Good news, there's no variables in our limits of integration. This is a product or quotient, if you will. So we have 1/5 integral 0 to 4 of u du times integral from 1 to 8 of dv over v. And I'm going to, this ends up being 1/5 ln of 8. Probably an extra line that's needed, but I was running out of paper, so I'll make sure that I show the steps when I upload the results online. This last bit is just straight up integration. The only part of this that's new is that we've learned about how to find that scaling factor.
Is that integral 1 to 8?
Yeah,
the
1 to 8.
innermost integral? Okay.
Yeah, 1 to 8. Yeah. Let me go and hit Enrique's question and see if I can make a connection with something that you've done in the past. So how might this work? So let's make a connection between what we're doing now and the conversion between rectangular and polar coordinates. So if you wanted to find the scaling factor to go from xy to r theta, you would use the formula that x equals r cosine theta and y equals r sine theta. So the Jacobian would be the Jacobian of xy with respect to r theta. So xr, x theta, yr, y theta. Substitute in all your partial derivatives, and it'll probably shock all of you that the Pythagorean identity sine squared plus cosine squared is going to come in. And we find that our Jacobian ends up being r. Our scaling factor ends up being the absolute value of that, but we always end up with positive r's, so we get to drop off that absolute value. So notice that the conversion from rectangular coordinates to polar coordinates that we worked on at the beginning of the class can be explained. That scaling factor could be explained geometrically. That's how we explained it 2 weeks ago. Or we can justify that formula by using this same scaling factor Jacobian concept. Enrique's question was, do we always have to do it in the order where we find the Jacobian of uv with respect to xy, and then we take the reciprocal of it? No, and here's a good example. Notice that here, the original definitions of the variables were already solved for x and y. And so since they were already solved in x, y, we could do our conversion, because this is going from the xy world to the r theta world. And the formulas are already set up to be able to find what's going on. Did that answer your question, Enrique?
Partially, I think.
So if you think about it, in the example that we were just looking at prior to this, we had u equal to x minus 2y and phi equal to 3x minus y. And so notice these equations are solved for the new variables.
Mm-hmm.
Since they're solved for the new variables, we ended up having to do the reciprocal thing.
Okay.
But in this polar world, we are solved for the old variables, x and y.
Mm-hmm.
And since we're solved for the old variables, we didn't have to do that reciprocal thing.
Okay. I'll just need a little bit of practice and then it'll solidify, but I get the idea here. Thank you.
Yeah, it just has to do with which direction. Worst comes to worst, you do everything right and you have your scaling factor exactly upside down, and that's like a 1 point easy thing. And I think everybody's going to figure it out long before there's a grade writing on it.
Cool.
Because that one's so cool and we're already there in the notes, you could do the same thing going from rectangular to spherical coordinates, except for you end up with a 3x3 determinant with a bunch of trig functions in it. And it's like it's not hard, but it's just kind of a total mess. You got to keep track of everything, multiply it all out. You keep using common factors. There's like yellow common factors and pink common factors. And you end up with a whole bunch of Pythagorean identities. And at the end of the day, blah, 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 all that stuff, you end up with your rho squared sine phi. And so we could explain that scaling factor going from rectangular to spherical coordinates geometrically. That's what we did in 16.5. Or we could explain it by making a reference to the Jacobian. Cool bit. Remember, the Jacobian here has no absolute value, but we need to have an absolute value in our scaling factor. And as you probably remember, rho squared will always be positive because because squares posify everything. And then we required our phi to be between 0 and pi. So sine phi is always going to be non-negative. And so this quantity will always be non-negative, which is why, again, in this case, we could ignore the absolute value, just kind of based on the way we've constructed things. Pretty cool stuff. Questions are ready for one more example.
One more?
One more it is. So the last, I think I've got this one set up so that the scaling factor comes out negative, but I ran out of time in creating my notes to work through this last one. So we will see whether we're successful. So in this case, we wanted to find the double integral of x plus y, e to the x squared minus y squared dA. We did our substitution. All of our limits come out really nice. The only thing we're missing is that scaling factor. So let's calculate it. So if we want to find that scaling factor, we're solved. What we want is the Jacobian of xy, our old world, with respect to where we're going, uv. That's what we want. But that would be a little bit of a pain to find, so let's not work quite that hard. So the easy one would be the Jacobian of uv with respect to xy, which will be the partial with respect to x, or 1, partial with respect to y, 1, partial with respect to x, 1, partial with respect to y, -1. And what is this determinant work out to be?
-2.
-2. So this tells us that the Jacobian that we want is -1/2. And our scaling factor will be the absolute value of this, or -1/2, absolute value of -1/2, or +1/2. Does that make sense? So we have to posify that scaling factor. That allows us to go back in and set up our integral. Got it covered up. 0 to 3, 0 to 2, u e to the uv times 1/2 dv du.
I'm guessing it's just a typo on this example, but it says x plus y equals 3 equals 4. Is that supposed to just be x plus y equals 3?
Probably.
Okay.
Is it on the handout? Where are you at?
Yeah, on the work along.
Nice.
You guys heard it here first.
Yeah, I can see
3
it.
equals 4.
Sweet. Yeah, heard it here first. No extra charge for that particular life lesson. Thank you for that one, Dame. Cool. So, and I'm not going to work through the integration here. At this point, it's just integrate, evaluate. The only challenge is finding the scaling factor. And then it's just a bunch of writing. Are there questions about this, or are you kind of ready for me to try to summarize and pull all this stuff together for you?